Every single morning, the exact moment you turn your key and hear your engine violently fire up, a totally brutal, invisible clock starts ticking down right under your hood. And the absolute worst part about this mechanical countdown is that 95% of the permanent, irreversible damage happening to your engine block doesn't occur while you are aggressively passing a heavy truck on the interstate. It doesn't happen when you are towing a massive trailer up a steep mountain grade. It happens in the absolute first 3 seconds after you start the car. You can buy the most expensive, premium synthetic oil sitting on the shelf, precisely match the numbers printed directly on your yellow oil filler cap, and still be pouring a liquid into your crankcase that is completely failing to protect your bearings. You honestly think you are doing the right thing. You completely trust the maintenance schedule, but you are silently financing a massive, multi-thousand-dollar engine rebuild on the installment plan. To completely understand why this is happening, you have to throw the standard dealership marketing brochures directly in the trash and look at the raw physical reality of how heavy metal actually interacts. Inside your engine block, oil protection physically works in entirely different regimes, depending on the exact physical stress the engine is under. Engineers classify these into 3 highly specific categories: hydrodynamic lubrication, mixed lubrication, and boundary lubrication. Hydrodynamic lubrication is the absolute ideal, perfect state. This is exactly what you want happening while you are cruising down the highway. This is when the incredibly heavy metal components are not supposed to physically touch each other. The oil pump constantly forces liquid under extremely high pressure directly between those metal parts. Because the metal surfaces are spinning incredibly fast, they physically pull the raw oil into a microscopic wedge. The heavy steel parts literally ride on an invisible, highly pressurized wave of oil. They physically float. But that floating effect relies entirely on the oil having enough physical structure, enough raw thickness, to hold the metal apart against the violent, explosive force of the combustion chamber pushing aggressively down on it. When you park your car in the driveway overnight and shut the engine off, the mechanical oil pump completely stops spinning. The extreme pressure instantly drops to 0. Over the next 8 hours, raw gravity relentlessly pulls that protective layer of synthetic oil directly down the block and right back into the bottom of the oil pan. The heavy steel crankshaft journals press heavily down on the soft aluminum main bearings, completely squeezing out whatever microscopic layer of fluid was left between them. When you walk out to your car the next morning and turn the key, you are not in hydrodynamic lubrication. You are trapped in boundary lubrication. This is the absolute mechanical danger zone. That protective hydrodynamic wedge completely collapses. To the naked eye, a highly machined camshaft lobe or a steel crankshaft journal looks like a perfectly smooth, completely reflective mirror. But if you take that exact same piece of expensive metal and put it under a heavy electron microscope, the physical truth is terrifying. It looks exactly like a rugged mountain range. The surface is entirely covered in massive, jagged peaks and deep, rough valleys. Engineers call these asperities. When you crank a freezing cold engine, the thick, heavy oil completely refuses to flow quickly. The metal is partially contacting the raw metal. Those jagged, microscopic steel peaks physically scrape and drag aggressively across each other without a solid fluid wedge to keep them separated. This creates an incredibly violent event called micro-welding. The intense, localized friction generates massive thermal spikes right at the absolute tips of those metal peaks. For a fraction of a millisecond, the heat is so extreme that the 2 pieces of heavy metal physically weld themselves together. But because the engine is aggressively spinning at 1200 revolutions per minute on a high idle, that microscopic weld is instantly, violently torn apart. Microscopic shavings of heavy bearing material are aggressively sheared off and washed directly into the oil pan. You are actively scoring the soft aluminum walls of your cylinder heads. You won't hear a loud explosion. The dashboard won't light up. It is an entirely silent, totally invisible cycle of wear. You don't blow a motor up in one violent weekend. You slowly murder it over 3 years using a series of tiny, invisible mistakes that you honestly think are completely harmless. This brutal boundary wear accounts for over 80% of the physical degradation your engine block will ever experience. It is the exact reason why some cars roll into my shop totally destroyed before they even hit 60,000 miles, while others easily push past 200,000 without a single heavy repair bill. And modern technology is actually making this cold start boundary wear radically worse. Almost every single modern vehicle rolling off the assembly line today uses gasoline direct injection. Instead of spraying fuel softly into the intake manifold like the old days, a direct injected engine violently forces raw liquid gasoline straight into the highly pressurized combustion chamber at thousands of pounds per square inch. When the engine is cold, the internal combustion is not perfectly efficient. Tiny amounts of that raw, liquid gasoline physically wash past the steel piston rings and drop directly down into your oil pan. Gasoline is a powerful solvent. It entirely breaks down lubricants. It heavily attacks the chemical base stock of your motor oil and aggressively thins it out. So, not only are you starting a completely dry, cold engine with heavy metal-on-metal contact, but the tiny amount of oil that finally does manage to reach the top of the cylinder head is entirely compromised by raw fuel. You are driving on heavy liquid sandpaper, heavily chewing up your own rotating assembly. Automakers try to fix this by mandating extremely thin, watery oil like 0W-16 or 0W-20, entirely because the heavy metal oil pump doesn't have to work as hard to push that liquid through the block. The engine spins slightly freer and the efficiency goes up by maybe 0.5%. The automaker mathematically passes the federal emissions test, dodges a massive fine, and gets to slap a shiny green sticker on the window at the dealership. But raw efficiency and heavy metal protection sit on completely opposite ends of the exact same physical spectrum. A thin oil is fantastic at reducing drag, but it completely fails to protect the internal components when you are stuck in boundary lubrication. Before we get completely deep into the exact physical compound that heavy aerospace and industrial engineers use to completely stop this brutal cold start wear dead in its tracks, let me know exactly where you are watching from today. Drop a quick comment down below with your city or state. I always read through them because the ambient climate you drive in completely dictates the raw physical stress your oil is actively taking. A guy trying to keep his truck alive in the brutal, triple-digit dry heat of an Arizona summer is fighting a totally different mechanical war than a guy doing aggressive cold starts in the freezing dead of a Minnesota winter. The local environment changes the entire chemical equation happening under your hood. And if you actually appreciate getting the unfiltered mechanical truth about how these machines operate instead of the standard corporate dealership script, do me a quick favor and hit that like button, and make sure you are subscribed to the channel. It tells me you guys want real garage knowledge, and it keeps me pulling the curtain back on the exact stuff the service writers absolutely refuse to tell you. Because the actual solution to this massive wear problem is not just pouring a thicker oil into the crankcase. The solution requires a highly specific, entirely different class of lubrication. It involves a specific chemical additive package suspended inside that fluid. We are talking about extreme pressure anti-wear agents. We are talking about a chemical that actively seeks out raw heat and violent friction, physically bonding directly to the jagged metal peaks inside your engine to create a totally unbreakable solid barrier. Let's pull the curtain completely back on the exact chemical compound that industrial engineers use to keep multi-million-dollar mining equipment and aerospace turbines from tearing themselves apart. There is an entire class of materials in the tribology world known as solid friction modifiers. And the absolute king of this category when it comes to internal combustion engines is a compound called molybdenum disulfide. Most mechanics and machinists just call it moly. If you walk down the aisle of your local auto parts store, you're going to see a wall of brightly colored plastic bottles promising magic horsepower and claiming to fix blown head gaskets. 99% of that stuff is total snake oil. It is highly diluted garbage designed to separate you from your wallet. But moly is not magic. It is raw, documented, highly tested mechanical chemistry. To understand why this specific compound is the absolute ultimate defense against the cold start wear we just talked about, you have to look at how it physically behaves under intense pressure. Traditional motor oil is a liquid. It works entirely by trying to float the metal parts away from each other. Moly does not float. It is a microscopic solid. When you introduce it into your crankcase, the engine oil simply acts as a carrier fluid. The oil transports these microscopic solid particles through the oil galleries, up into the cylinder head, and directly into the tightest, hottest clearances inside your rotating assembly. When those jagged microscopic steel peaks, the asperities we talked about earlier, violently smash into each other during a cold start or under a heavy load, they generate a massive, localized spike in raw heat. That specific spike in temperature triggers a tribochemical reaction. The moly particles physically bond to the raw metal. Look at the molecular structure of molybdenum disulfide. It is built in flat, hexagonal layers. Think of it exactly like a microscopic deck of playing cards. When extreme physical pressure pushes down on those layers, the cards effortlessly slide and slip right off each other. They absorb the brutal mechanical shear force, so your expensive steel bearings don't have to. Instead of your crankshaft grinding its own metal away, it simply slides on those sacrificial layers of moly. Let's look at the absolute raw math on this because the numbers are staggering. If you take two pieces of dry, machined steel and rub them together, you have a friction coefficient of about 0.6. It is incredibly high. If you put a layer of premium synthetic motor oil between them, the number drops down to about 0.1. The oil does a decent job, but when you properly treat those exact same steel surfaces with a solid moly lubricant, the friction coefficient plummets down to 0.03. You are actively reducing the mechanical resistance inside your engine block to a fraction of what standard liquid oil can physically achieve. That is an absolute canyon of a difference when you multiply it by thousands of revolutions per minute, every single day, for a decade. I want to know right now, who watching this is completely terrified of pouring anything other than plain motor oil into their block? Be honest, drop a comment down below. Tell me if you think all additives are pure snake oil, or if you actually run a specific friction modifier in your daily driver. I know a lot of guys have been burned by cheap gimmick products in the past, so I completely understand the skepticism. Let me know your exact stance in the comments, because I see the physical results of this chemistry in my repair bay constantly. I have two specific customers who do full-time rideshare driving in the exact same model of a naturally aspirated 1.6-liter Japanese commuter sedan. These guys practically live in their cars. They put down insane mileage, doing constant stop-and-go city driving, dealing with endless idling, and shutting the engine off dozens of times a day. It is the absolute worst, most grueling physical environment for an internal combustion engine. Driver A is a total purist. He firmly believes the manufacturer knows best. He strictly uses the factory-recommended ultra-thin 0W220 oil, changes it exactly when the dashboard light tells him to, and completely refuses to use any friction modifiers. Driver B took a totally different route. He buys a slightly thicker base oil to combat the intense city heat, and since the car had 30,000 miles on it, he has consistently treated the crankcase with a high-quality solid moly lubricant. Driver A brought his car into the shop last winter with 220,000 miles on the odometer. The engine had a harsh, stubborn rattle on startup. It was drinking oil. I pulled the spark plugs and ran a manual compression test on the cylinders. The numbers were entirely shot. The microscopic scraping on his cylinder walls had permanently worn down the steel piston rings. The blow-by was massive. His engine was completely exhausted and mechanically done. Driver B's car is currently sitting at 380,000 miles. It still runs the original timing chain. It still holds rock-solid cylinder compression across all four banks. The only physical difference between those two identical machines is how they managed boundary lubrication during those critical, unlubricated moments. driver B's engine survived because the solid moly compound actively filled in the microscopic valleys on his cylinder walls. It essentially plated the metal. It turned a rough, jagged, abrasive steel surface into a smooth, glass-like finish that actively rejected friction. His piston rings simply glided up and down the bore instead of physically chewing the crosshatching to pieces. You see this exact same mechanical reality play out even faster in the diesel world. I have a guy who hotshots heavy equipment using a 1-ton diesel truck. He routinely hauls 15,000-pound steel trailers through the mountains. When you drag that much weight up a 6% grade, your exhaust gas temperatures climb to completely terrifying levels. The massive turbocharger bolted to his engine block is spinning at over 100,000 RPMs, soaking up all of that raw heat. When he pulls off the highway into a rest stop and shuts the rig down, the oil pump stops. The liquid oil left inside that blazing hot turbo bearing physically cooks. It boils off and leaves the metal totally vulnerable for the next time he turns the key. Before he started treating his block, he was tearing through a factory turbocharger every 80,000 miles. The bearings would literally score themselves to death from the dry, hot starts. We completely flushed his crankcase and introduced a heavy dose of solid friction modifier. The change wasn't just a slight improvement on paper. He could physically hear the difference. The heavy, metallic diesel clatter on freezing cold mornings entirely smoothed out. The engine felt noticeably less strained, pulling away from a dead stop with a heavy load. And more importantly, the oil analysis reports he sent off to the laboratory came back showing his iron and aluminum wear particle numbers had dropped completely off a cliff. The solid compound bonded directly to the turbo shaft. It didn't care that the liquid oil had drained away overnight. It didn't care that the metal was sitting at 500 degrees. The physical plating remained totally intact, perfectly separating the steel shaft from the brass bearing until the mechanical oil pressure could catch up. A lot of drivers will hear this and instantly ask a totally logical question. If this specific chemistry is so incredibly good at stopping engine wear, why don't the massive billion-dollar oil companies just put it right in the plastic jug to begin with? They actually do, but only in extremely microscopic amounts. You have to completely understand the business model of motor oil. When a refinery blends a batch of synthetic oil, they are not formulating it to make your specific engine last 500,000 miles. They are formulating it to perfectly hit a specific price point on a retail shelf and to strictly satisfy the latest environmental API specifications. Molybdenum is an expensive raw material. Heavy concentrations of solid friction modifiers simply eat into corporate profit margins. Furthermore, automakers actively pressure oil companies to strip certain heavy anti-wear additives out of the bottle because they claim those chemicals can slightly reduce the lifespan of modern catalytic converters over the course of a decade. The entire industry is purposely trading the physical-mechanical lifespan of your heavy steel engine block for a fractional improvement in tailpipe emissions and a cheaper retail price on the shelf. They are formulating oil for a driver who leases a crossover for 36 months and trades it in before the warranty expires. They are absolutely not formulating it for a guy who actually wants to own his machinery outright and keep it completely out of the junkyard. If you want absolute, uncompromising mechanical protection, you have to actively take control of the chemistry yourself. You cannot blindly trust a corporate formulation designed by an accountant. But before you run out to the garage and start dumping random bottles of additive into your valve cover, you absolutely need to understand that there is a highly specific, totally critical method to applying this chemistry. If you use it in the wrong engine, or at the exact wrong time in a car's life cycle, you can instantly create a massive, highly expensive mechanical nightmare. A lot of guys see the raw mechanical data on solid friction modifiers, get totally fired up, buy 3 massive bottles of the stuff, and dump it straight into a brand new engine with barely 500 miles on the odometer. That is an absolute, catastrophic mistake. If you do that, you just completely guaranteed that your brand new motor will violently burn oil for the rest of its physical life. You have to understand the intense physical environment of a completely new engine block. When a motor is freshly built at the factory, The piston rings do not perfectly seal against the heavy steel cylinder walls. They need raw, aggressive friction to physically wear down and seat themselves properly. The heat and the scraping entirely shape the metal rings to the exact microscopic dimensions of the cylinder bore. If you prematurely introduce a highly advanced solid boundary lubricant like molybdenum disulfide before the engine is fully broken in, you entirely glaze the cylinder walls. You make the metal so incredibly slick that the piston rings simply hydroplane. They completely refuse to seat. You will have massive blow-by, heavy oil consumption, and terrible compression forever. You actively ruined the machine by trying to protect it too early. You always wait until you cross at least 10 or 15,000 miles before you introduce solid boundary chemistry. And right on the opposite end of the spectrum, you have the guys treating this chemistry like a magical resurrection spell for a totally destroyed motor. I had a kid tow a heavily beat-up domestic hatchback into my lot last spring. The engine had a deep, aggressive rod knock that was so loud you could physically hear it echoing down the street. He hopped out of the truck and proudly told me he just dumped $100 worth of premium solid friction modifier into the valve cover, totally expecting it to quiet the engine down and save the block. Solid lubricants are not liquid mechanics. They do not magically regrow missing heavy metal. If you entirely ignored your oil changes, completely starved the engine of fluid, and physically chewed your bearing down to the raw copper base, no chemical in the world is going to rebuild that shattered steel. You are staring at a completely mandatory engine replacement. This chemistry is an aggressive, proactive defense shield. It is absolutely not a cure for heavy mechanical neglect. You also have to strictly look at the exact engineering of the specific car sitting in your driveway, because not all metal is treated the exact same way. If you look at the heavy American V8s pushing massive torque out of a heavy-duty truck, those big displacement blocks absolutely love solid boundary protection. The internal clearances are slightly looser, the sheer physical mass of the rotating assembly is huge, and the bearing loads are totally violent. You treat a hard-working American truck with a solid additive, and the physical wear metals showing up in your oil filter will instantly plummet. Japanese blocks from Honda and Toyota are entirely different animals. They run incredibly tight tolerances right from the factory floor. They are already engineered for maximum mechanical efficiency, but even Japanese engines heavily suffer from cold start boundary wear. When you add a top-tier solid suspension to a high-mileage Japanese motor, you basically freeze the internal wear right where it currently sits. You actively lock in that legendary factory reliability and extend the life of the rings out to 300,000 or 400,000 miles. Then you have the highly complex, massively over-engineered German cars. Modern BMWs and Audis run extremely sensitive variable valve, timing, solenoids, and entirely rely on highly specific oil pressures to operate tiny, laser-drilled hydraulic tensioners. You have to be incredibly careful here. You never dump a cheap, unverified, totally random powder additive into a German engine. The powder will actively clump together, violently plug the microscopic oil screens, and entirely destroy the top end of the motor. You only ever use a highly verified, fully suspended colloidal moly that is physically engineered to pass directly through the pores of a modern oil filter without catching. When you finally decide to pull the trigger and physically treat your engine, the actual application method dictates entirely whether it works or totally fails. You do not just walk out to a freezing cold car on a Tuesday morning, dump a bottle into the plastic filler neck, and leave the car sitting in the driveway. This highly specific chemistry absolutely requires intense thermal heat and heavy physical pressure to properly activate and bond to the metal. You take the car out on the interstate. You drive it hard for 20 minutes. You get the heavy metal block and the engine oil completely up to full, blazing, hot operating temperature. The metal pores physically expand. You pull back into your driveway, pop the hood, and while the engine is still totally hot, you pour the exact recommended dosage of the friction modifier directly into the valve cover. Then, you instantly jump right back into the driver's seat and put the car back on the highway for another 20 minutes. You are actively forcing the mechanical oil pump to violently circulate that highly concentrated solid compound through the entire block. You are aggressively pressing the moly directly against the jagged steel asperities while the internal temperature is at its absolute peak. That is exactly how you force the tribochemical reaction to occur. You bake the protection right into the steel. When you do this correctly, you execute a massive mechanical reset on your engine's lifespan. You have to totally shift your mindset. You aren't permanently fixing the car. You are actively slamming the brakes on the aggressive degradation process. Every single time you cold start an unprotected engine, a microscopic peak of heavy steel is violently sheared off. That broken piece of metal instantly becomes a free-floating, microscopic abrasive rock totally trapped inside your oil. It acts exactly like a tiny diamond, brutally scoring your soft bearings as it circulates. By actively laying down a sacrificial solid layer of molybdenum, you entirely stop those metal peaks from breaking off in the first place. You completely kill the chain reaction of internal wear. But this is exactly where some drivers get entirely overconfident and do something highly destructive. They treat the additive like an absolute, totally impenetrable magic force field. A guy treats his block with a premium friction modifier, the engine starts running incredibly smooth and quiet, and he suddenly thinks he can completely ignore his basic maintenance. He assumes he can leave his engine oil trapped in the pan for 15,000 miles because the metal is supposedly bulletproof. If you completely ignore your basic oil change intervals, your heavy paper air filter, or your pressurized cooling system, your engine is still going to violently blow up. The solid lubricant only protects your bearings against raw boundary friction. It does not magically stop unburned liquid gasoline from entirely washing past your piston rings and diluting your oil. It does not prevent thick, heavy, acidic sludge from permanently baking onto your timing chain guides. You still have to do the physical, dirty work. You pull the oil drain plug absolutely every 5,000 miles. No exceptions, no excuses. You get the heavily contaminated fluid totally out of the block, and you maintain the solid boundary layer exactly as the chemistry demands. Engines do not just violently die on a random afternoon for absolutely no reason. They are murdered in absolute silence, completely out of sight over thousands of totally routine morning commutes. Every single time you crank that key, the heavy internal metal is violently crying out for a physical barrier that cheap, ultra-thin factory oil simply cannot provide. The guys who confidently push their daily drivers past 500,000 miles don't just sit around hoping for good luck. They actively dictate the exact mechanical environment inside their engine block. They refuse to trust long service intervals, and they totally refuse to blindly follow a piece of cheap plastic sitting under the hood. If this deep dive completely changed the way you look at the raw physical friction happening inside your engine right now, do me a massive favor and hit that subscribe button. Drop a quick comment down below and tell me the absolute highest mileage you have ever personally seen on an original, unopened engine block. I read through every single one of those stories, and I guarantee the cars hitting 400,000 miles are not doing it purely on totally unprotected cold starts. Take absolute control of your heavy machinery. Stop relying entirely on liquid oil to do a solid metal job, and I will see you in the next one.